Welcome to this talk. My name is Marvin Drees and I'm from 9 Elements Cybersecurity. Today we're going to talk about UBMC, the next generation BMC software stack born from the uroot ecosystem. So first of all, what even is a BMC? Because some of you might not be yet familiar with that term. Well, the acronym stands for Baseboard Management Controller, and it's usually an embedded ARM system, which is found on many workstations and servers. As you can see in the picture on the right, it's tightly coupled within the main circuitry because it's directly integrated onto the board. It allows interfacing with the host by basically reading out sensory data or controlling fans and other hardware parts. It also allows the management, so not only the monitoring, and therefore you find these on pretty much any server board on a hyperscaler or on workstations that needs to be constantly controlled from outside. So let's get to the current landscape, because there are, of course, BMC solutions already out there. One of them, and the most known open source one, is OpenBMC, a project started by Facebook years ago. It's also probably the mostly adopted one right now because it's being run on very much of the OCP hardware stack and other big vendors. Another more special open source solution that you might not yet heard of is Kestrel. It's being developed by Raptor Engineering, and it's running fully in an FPGA and uses OpenPower instead of ARM. Another of the more proprietary ones that we can find out in the wild are AMI Megarec, which is at least the open edition based on OpenBMC as well. Insight Supervise, which can also be found on several boards, or basically a lot of other ones like Dell iDRAC or whatever HP is using, mostly OpenBMC nowadays, I think, and other solutions, because everyone that is producing servers needs, of course, some sort of BMC stack. So let's get to the topics of this specific talk. Well, first, we'll start with the build system comparison, and it's not going to be as boring as you might expect it. Then to the main architecture of UBMC. I'll also talk quickly about uroot and Go BusyBox, which is the ecosystem this is comprised about, as well as gRPC versus IPMI. And at the end, we'll get a quick look at the roadmap and the history of this project so far. So now to the build system. I'd say first we should start with what the other ones are using, like OpenBMC is using the Yocto project. The Yocto project uses BitBake and a layer system, or meter layer system, or they call it, I guess. So you have several layers, and each of them gets stacked together, like you might know it from kind of Docker files. We also have these layers that then make the image at the end, but this time it's only during build time and not during execution time. One of the downsides, and the major downside that we found during development of OpenBMC, is it's pretty resource intensive and slow. So building an OpenBMC image can take upwards to hours if your machine isn't strong enough. It's also not that easily extensible because the meter system uses its own kind of syntax, and you need to read a lot of documentation, which is not that easy to find, to be honest. But now to the good sides of Yocto. It's a dedicated build system for embedded Linux distributions, and it's already widely adopted in the industry. A lot of IoT and hyperscaler vendors use it for their embedded systems, and it has a lot of cool features like reproducible builds and always having a pretty modular tool stack. And as said, it's much more mature already. So now to what is OpenBMC using, to what is UBMC using. Well, it has been using makefiles before, but everyone that worked with makefiles knows that pretty hard to actually write makefiles in the correct way, and to extend them to anyone that has not yet been working with makefiles can get kind of hard. So one of our other projects has been using Taskfile, a pretty more modern approach to that. Next to the fact it's written in Go, that means it's fast and can use the native concurrency of your machine already. It has a pretty easy configuration using YAML files, which are not only easy to read and write by humans, but also easy to parse. And it poses itself as a replacement for Make. So it was pretty much already there made for the job. It only automates build tasks and has a built-in shell interpreter, so you can theoretically run it on a system that doesn't even have a shell. And it's also easily extensible. The upstream developer listens a lot to our feedback and already implemented new features for us, and you can easily contribute as well. Also, it's written in YAML, so if you know how to write YAML, you can also write now new task files. And if you don't know how to write YAML, just look at a few of our task files and you will learn it in no time. Now to the basic architecture itself. Well, first up, we boot up using Linux boot, one of a project that might be familiar to others. And if it's not yet familiar to you, Linux boot basically just allows booting the system up using only Linux and its included drivers. The user space that we have is comprised of a single executable file. This is realized using Go BusyBox, and other files that we then can call to mimic a full-fledged system kind of is using symlinks that all point to that one binary. This is basically how BusyBox is doing it, and it's not really a very new concept, but now it's also possible in Go using Go BusyBox and uroot. The management of the BMC stack then happens via UBMC control, which is an gRPC tool. Usually you might get used to using IPMI tool or things like that, which are written in C and only can interface with any BMC that's using IPMI, and the syntax is, well, not that yet user-friendly, I'd say, or other things like Redfish, which also aren't really user-friendly in my opinion. Also, there's a metrics endpoint, but we'll get to that later. In addition, you can also get access to it using an in-process shell using SSH or physical access if you have that to that server. But usually you don't have physical access, so SSH would be then the way to go. Now, Linux boot itself can be implemented in many ways. In our case, it's a bootloader that's made of the Linux kernel, of course, and that runs then a now self-written bootloader using Go, and that verifies the signature of the runtime kernel and the user space. If the signature verification succeeded, then we use kexec to boot to the runtime kernel and dispatch of anything else that was previously there. In the past, we were using OpenPGP for verification, but the user experience of using OpenPGP wasn't that great, I'd say. So there are much more modern alternatives, like in our case, Minisign, which was developed after, I guess, OpenBMC Signify, which is using elliptic curves to check out the verification. Another way to do that nowadays would be to use SSH keys, but we figured that using Minisign saves a bit of space instead of having a fully fledged SSH verification daemon in there. So that's just what we've been using. Future versions could also check the UBFS authentication as well. This is a kernel feature that has been added rather late, I think, and because most of our systems use spy flashes that can use UBFS, we can use that kernel feature as well. And if UBMC isn't really storage comprised, and if the storage capacity of your BMC is all right, then you can also go for an AMD update scheme that we plan to implement. So this way you can have graceful updates and don't need to worry that something that during an update happened could crash your whole stack, because you can always go back to the other partition. That, of course, requires a little bit of extra space and would only be available on more modern BMCs. But in this case, modern means like anything past 2016 or so. So now let's get to Linux boot on ARM. Well, because UBMC is mainly targeting ARM system, we need to look at how Linux boot actually works on this machine. Well, in QEMU, our testing infrastructure, we can just use direct kernel boot, but what is on real hardware? Well, on the AST2400 and 2500, which are our main targets, a bit of open source assembly code in our repository is able to train the DRAM and set up a few minimal systems that then allow us to boot directly into a Linux kernel. Other future SoCs could then use the LBBR standardification, which stands for Linux Boot Baseboard Requirements and allows booting the Linux kernel directly from TFA, which stands for Trusted Firmware on ARM v8 SOCs. After the boot up, the user space comes into play. As I already said, it consists of a single static Go binary. This is realized using Go BusyBox. Previously, we used the uroot include build system, but there were a few shortcomings that Go BusyBox, which is also hosted on GitHub under the uroot organization, seems to fix. So there was also the issue that why not use several binaries instead of one large? Well, the thing is, with Go, several small binaries aren't really possible because every binary has to keep the Go runtime. That has the benefit of not relying on any system libraries, but also the downside that every static binary grows in size and we're on an embedded system. That means we can't really afford losing much of that precious storage capacity. So a single binary only packs a single runtime, therefore allowing the most space efficient setup. It also makes resource management much easier because we don't need to rely on any scheduling, as the Go compile time uses the runtime packed into it so that we can have lightweight threads like Go routines that make management of the in-process services much easier. The only downside now is that the Linux kernel security modules like landlock and SE Linux are a bit harder to implement because those usually expect to work on on their own binaries, so that have like this binary can get storage permissions while the other binary cannot. And now we only have a single binary, so it's a little bit harder to implement, but not impossible. Now let's get to interfacing UBMC. This is what makes it more unique. So we have an included Go shell, which is Elvish in our case, which is the most fully featured shell that we could find right now. It's accessible using SSH and serial connection. In this case, it's, as you can see on the right, we have the shell access using a serial connection to our virtual machine. We can also use UBMC control to interface with it. I guess the screenshot isn't that high res, but if you zoom down, UBMC control can be used to basically display the version right now, display the services available, and then control the hardware and also read out sensory data. Another possibility to interface with UBMC is using the metrics endpoint. It's using the open metrics format, and this data can be scrapped, e.g. using Prometheus, but we'll get that in a minute. So now gRPC versus IPME. Well, unlike gRPC, IPME is simply a specification. That means it's a hardware interface that consists of several standards. Well, in our case, RPC, so remote procedure call, would be kind of the more equivalent to IPME, but we use gRPC, the Google's implementation, as it's the widely adopted one, basically. We also use gRPC with parts of the specification. So the hardware interfaces that IPME is talking to is also being reused to some degree by gRPC in this case, but we're not using the host to BMC infrastructure that IPME is there deploying. The main benefit that gRPC gives us over IPME is that we can go for generic tooling. So UBMC control, our gRPC client in this case, can be used both on the BMC and remote client side. So you have only one software stack that works on both sides and can interact with the system. This makes it not easy to maintain, but also makes it easy to reuse on different operating systems, because gRPC has the benefit of being written in protocol buffers, and protocol buffers can easily be ported to different languages. So you can just use the generator of your choice, take the protobuf files from our repository and recompile them in whatever, like Java, C, or even Rust. But if you don't want to go for your own client, just use UBMC control. And as it's written in Go, it should work on Linux and Windows and Mac by simply changing out what the compiler should compile for. Now to the metrics endpoint, one of the most interesting pieces, I'd say, for all of you DevOps out there. UBMC exposes an open metrics endpoint. That means, as you can see in the screenshot on the right, on a /metrics URL, metrics can be scraped. And that is in a format that is widely adopted in the industry already. You can use Prometheus and other time series databases to collect this data. Don't get surprised about that, not secure that. It's just because we're using a self-signed certificate right now on the BMC, as that is what most BMCs been using. But there's another feature that we can tell that is really good. No, but there's another feature of this BMC that has not yet been talked about very much. So we have certificates that are auto-renewed and can directly interface with Let's Encrypt. Some of you might know the Caddy web server, and it's kind of certificate magic that is being used there. Well, the library is actually called Cert Magic, and we're using it for auto-renewal of certificates, so you don't need to worry and maintain some valid certificates on your BMC stack. Let's now get to the history of UBMC. Well, it started in 2018 and was there published by Christian Svensson, who was at that time working in the Google security department. I guess he started this as a proof of concept on one of the Quanta Leopard boards that they have been using there, which is also using an AST 2400 socket. At the beginning, it was using U-boot, and later on switched to Linux boot. But not only did it switch to Linux boot, but it also changed few core structures, and later on, the project kind of got abandoned for a few years. Then I picked it up again, and the first thing I saw that the mate system was kind of only made to work with the one specific board. So I wanted to make it more generic and more easily implement new targets. So I replaced make with task. After that, cleaned up the code that was after the years got broken and fixed it to a now working state. So now the roadmap and the planned features. This is basically the most interesting part of this talk, I'd say. More hardware support, of course, because right now we only have QEMU support. Well, QEMU support is good, but we don't really have hardware to test this on other than the AST 2400 and 2500. Well, the 2500 is now the mostly adopted SoC for BMCs, I'd say, because you can find this on basically any Supermicro board or any board that you find out there, because any ASRock board and all the boards I came across have been using some sort of A-speed socket. We do have support for these yet, and I also plan to improve the support for that, but still, it's not that generic. You can't just like use it as an operating system that you put on a USB stick and then install your ISO. As with firmware, you always need specific hardware support and specific board support. I try to make this as generic as possible, but for now, only supporting AST 2500s means that if you want to hack on UBMC, you need a pretty expensive server or workstation board. Well, having a Raspberry Pi as a hardware target would make it much easier for people that don't have a high budget to hack on the project and already see their efforts being put into reality. Another thing that we plan to do is a UBMC graphical mode. The reason for that is if you used the IPME tool before, you know that only having this super long command line arguments, well, does work and also works good in scripts, but if you need to interactively read out data and control your BMC, where you don't basically have access to basically some sort of web interface, you need some sort of graphical mode to easier get used to working with the BMC. And there are several ones that are lightweight, and I plan to implement one of these in an N-cursor style. So if any one of you already configured a Linux kernel, this might be something that then gets familiar to you. Also, proper BMC functionality. Well, yes, UBMC works, but the basics are there. It's just not yet that fine-tuned. So we need more hardware control, like different interfaces. For now, fan control is there, but also needs to be improved to work on basically PWM interfaces or fans that are used on other interfaces as well. Also, voltage and temperature monitoring using regulators should be implemented for much more hardware targets and in a much more generic way. Things that are also not yet there are serial over LAN, but won't be long after this talk until these features get implemented, actually. And another thing that might be the highest challenge of them all is KVM, not the virtual machine KVM, but keyboard, video, and mouse, so that you can have control over your machine like you are basically physically there. So you have the output using the BMC's video stack and use the I/O of the keyboard and the mouse, which is then emulated on the host part over, for example, a web interface or UBMC control. Another thing that is not yet there is host firmware update and USB emulation. because using host firmware update, you can then simply flash on new releases of core boot or your favorite firmware stack and use USB emulation to then emulate an ISO image or other operating system image that can be used on your server to directly boot up. One of the things that we are also lacking is a web UI, but it should be an optional web UI because UBMC, or rather correctly, micro BMC, should be as small as possible. So having a web UI with all the assets isn't really what our goal would be. But we figured that a lot of people actually control their BMC using a web UI. But if we implement a web UI, which we will definitely do in the not so close future, the API should be the same as UBMC control is already using. So if anyone is implementing a feature for UBMC control or the web UI, it can be directly reused on either one. Another thing that we still need to do is simplify and slim down the boot process. Yes, Linux boot is already pretty fast, but we can make it even faster. And one of the things that we have been thinking about is using even Go on the reset vector. So the first instruction that the machine gets is already using Go, therefore guaranteeing higher memory safety and native concurrency. Now, one of the things that I still prepared is a demonstration. Because using a demonstration, one of the things that I've now prepared is a demonstration of the system. Right now, there isn't really that much to see because it's still in the maintenance mode that UBMC is not yet production ready. So you need to still wait a few more months or years, depending on how fast the user base grows, so that we can develop faster and make this actually a usable product. As of right now, it's still kind of in a proof of concept state, but you can see for yourself. This process also demonstrates task file. As you can see here, cleaning up all the build artifacts that are there and then building the whole system. Not only can you see what is happening in a much clean way, then for other build systems, it's also happening pretty fast. So right now, all the user space executables have already been built. And the most part that this process is taking up All right, let's start the demonstration again. All right, I've also prepared a demonstration for you here. Right now, UBMC is not yet in a workable state that I would recommend you use in production, but rather still a proof of concept. This would indeed change in the coming month, depending on how fast the user base grows and how fast the code is actually developing. But it already does boot, and you can already see the system in action. I've prepared a little ASCII demo that also the link will be in the slides for anyone to watch it later on. This demonstration will not only show the boot up of the system, but will also show how the build system is building a UBMC image from scratch and then booting it directly on. There you can see that first we wipe all the build artifacts that are still there from my previous work and building it from scratch again. Building the Linux bootloader, the init.ramfs, and all the user space basically just takes a few seconds. So as you can see, having only a single Go binary and other tools around it makes the build process quite fast. Then we pack up the rootfs, and after the rootfs has been packed, the system immediately boots up. All right, small cut here and again here. Okay, after the rootfs has been built, this system will directly boot up. The good thing about this process is that the slowest part of it will be building the Linux kernel. So if you built the Linux kernel before and the configuration is pretty minimal, you know it will take a few minutes. I've actually benchmarked this on my small ThinkPad, and the whole build system just took about, well, I guess 5 minutes for the whole process, and most of this was downloading actually. So I'll pause it here real quick because, as you could have seen, There were two kernels already booting up. The first one was then verifying the signatures of the second one. After everything passed, the second kernel has been booted and then jumps us into uroot. Uroot is our minimal build tool for this case and then launches our UBMC software stack. In the future, we might even need to exchange the init system of uroot with a much more slimmed down one to increase the boot speed even further. After UBMC has booted up, you can see in the logs already what has been done. So our system hardware has been initialized, our GPIO drivers are getting started up, the fan subsystem runs, and the UART console is now running at the correct baud rate because we're already viewing the system using the serial console. After that, the trusted time is going to be fetched because one of the main features of UBMC is actually to care about time control. Having insecure time on your BMC can mean that an attacker can forge certificates and other data to basically get the BMC to reject your certificates and fall back to an insecure channel. Then being able to do man-in-the-middle attacks and snoop what BMC data is being sent. To prevent things like that, one of the most overlooked protocols is the time protocol, and UBMC is only using trusted time. Therefore, if trusted time cannot be achieved, any communication to the outside will be halted until trusted time is achieved. So it will retry that several times, and if it is not able to get any way of trusted time, it will then just simply reboot itself and see if it can get that. Otherwise, the local communication via serial will always be online, because if you're at the machine physically present, then you can even trust the machine using, well, the wires to the machine, because that is already a trusted channel. You are at the machine and you're working with the right machine. After that, the certificate is being generated, in our case, just a self-signed one, because I did not really anticipate generating certificates for each of my tests for Let's Encrypt, but the infrastructure is already there. So you can use one of your favorite DNS providers and immediately verify your BMC, get a certificate from Let's Encrypt, and have it automatically renewed. You can see here that after trusted time has been achieved, in our case using Cloudflare's Roughtime protocol, the system now checks Google, but sees that the time it gets from the leap-smeared NTP server from Google seems to be too early. Well, I've just forged the time to be an hour off, and an hour off was already a sign that someone was tampering with the time. So it tries to talk to each of the Google time servers, but sees that something is off, and then simply rejects the time it gets from those. But we already got trusted time from our Roughtime server, and just take that time now. After we got our trusted time, I'm not yet dropping into a shell because one of the issues that you might see in a minute is that the only public Roughtime servers that are still there, from Cloudflare, Google, and some private ones, are not yet adhering to the latest standard, because Roughtime is still an IETF draft and not yet an RFC. So one of the issues is that not being an RFC means the standard can be incompatible with old versions, which we can see here. So I've hosted myself a modern Roughtime server that adheres to the latest protocol that we could get a trusted time from. So one of the issues here is that we might use NTS now, so network time security, but either way, trusted time is one of the main features that we don't want to lose ever. So if you now got that, I can immediately drop into a shell, and you can see that that shell basically works as any shell you've been used to as well. You have your basic controls, and now I'm using UBMC control to display what services are there. In this case, we can use reflection services and the main management service. The reflection service gives us information about what we're actually sending there, and the management service, well, it's managing the BMC basically, so that's speaking for itself. The last thing you see there is me just getting the version to verify that it's the correct one, and then shut down the BMC stack. All right, that's for my short demonstration. Now, a few project links and resources, because we already reached the end of this presentation. Of course, check out our GitHub under the UROT organization, where you can find UBMC. UBMC's website, of course, already telling you about some features about it and linking to the documentation, and the Linux Boot website, because right now Linux Boot is one of the main components that we are still using in our system. Therefore, check out Linux Boot as well. Thanks everyone for listening, and I hope you still aren't falling asleep. Have a great time on the OSFC and see you around next time.